Welcome back. This is section 2.4 of the text, box plots and quantitative/categorical relationships. I've divided the section up into three pieces: detecting outliers, box plots, sometimes called box and whisker plots, and finally, side-by-side box plots. Let's begin by studying a subsection called detecting outliers. And before we get started, let's just remember that an outlier is a value in the data set that appears to be removed or separated from the bulk of the data. I think it will be helpful to start with an example. So let's go to StatKey and load the file Descriptive Statistics and Graphs, one quantitative variable, mammal longevity. And this time we want to study the question, which mammal's longevity appears to be outlying? That is, which mammal's longevity appears to be removed or separated from the bulk of the data. So we'll go to StatKey, one quantitative variable, and we'll see that the mammal longevity file is the default file. That's the one that loads automatically. And when we look at our dot plot, we can see that the bulk of this data is coherent. It hangs together fairly well. There is one value here on the right, which is the elephant with a 40-year lifespan that appears to be separated or very different from the bulk of the data. So we would be suspicious that the elephant's longevity is an outlying value. But the question is, how can we determine if this is in fact an outlying value? Is there a rule that we can follow that would help us determine whether or not that is in fact an outlying value? So we're going to use what's called the IQR method for detecting outliers. Remember, IQR stands for the interquartile range. That's Q3 minus Q1. We call a data value an outlier if it is either smaller than Q1 minus 1.5 times IQR or larger than Q3 plus 1.5 times IQR. So how I want us to think about this is that we're taking the interquartile range and we're blowing it up or fattening it up by a factor of 1.5. That value is being subtracted from Q1 to form what I'll call the lower cutoff, and it's being added onto Q3 to form what we'll call the upper cutoff. So any elements in the data set that fall below the lower cutoff or above the upper cutoff are going to be labeled outlying values. Hopefully this will make sense once we look at a few examples. So let's take a look at this example. A small tech company, ByteGenics, has a mixture of job types: marketing, sales, programming, administration. The 5-number summary of the salaries at ByteGenics, and these are in thousands of dollars, is given below here. So we can see that the min is 59 and the max is 177. The median salary is $71,000. We've got a Q1 at 68 and a Q3 at 78.5. The question for us is, does this salary data contain outliers? Explain. Now, we're going to go to the overhead camera and work out the details in this example. So please join me at the overhead camera to see the exciting conclusion of this problem. In solving this problem, the first thing we're going to want to look at is the interquartile range. So we're going to want to calculate Q3 minus Q1. Let's take a look at that calculation. So the IQR is simply going to be 78.5 minus 68, and that's going to equal 10.5. Now remember, that's just the beginning. We have to take that IQR and we have to expand it by 1.5, by a factor of 1.5, to calculate our thresholds. So now we're going to calculate 1.5 times the IQR. And so that's going to be 1.5 times the 10.5. We have to fatten it up, if you will. And that gives us 15.75. Now, what do we do with that 15.75? We have to add that on to Q3. We have to subtract it from Q1, and those will produce our cutoffs. Anything below 68 minus 15.75 is outlying, and anything above 78.5 plus 15.75 is an outlying value. So let's calculate those two cutoffs. So we take 68 minus 15.75, and that's going to give us a lower cutoff at 52.25. We take the 78.5 plus 15.75, and that's going to give us an upper cutoff at 94.25. So this is our lower cutoff. And this one is our upper cutoff. Any value that's falling below the 52.25 will be considered an outlier, and any value in the data set that's above 94.25 will be considered an outlying value. Now, when we look at our 5-number summary, we can see that the smallest value in our data set, our min, is 59. And so we can see that there is no value in the data set that's falling below the lower cutoff. On the other hand, when we look at the 5-number summary, we see that there's at least one element in our data set that's as big as 177. So we know for sure that we do have at least one outlying value. We have at least one value that's exceeding 94.25. Now, how many outlying values we have, we don't know. We just know that this salary data contains at least one outlier, namely this maximum value. Okay, let's return to the class notes. Let's work one more problem in outlier detection using this IQR method. This time we want to go to StatKey, load the file descriptive statistics and graphs, one quantitative variable, mammal longevity. This is the data set we just looked at a few minutes ago. Now the question is, does this data set contain outliers? Explain. Now remember, when we looked at this data set before, we looked at the elephant with that lifespan of 40 years, and it looked suspicious. It looked like an outlying value. Now we want to submit this to a rigorous test. So let's take a look at the data again. Here's that data set, mammal longevity. And now we want to concentrate on using the IQR method to see if this elephant here at 40 years is in fact an outlying value. So I'm going to use the Desmos scientific calculator to help us do some of these calculations. Let's do the first bit is to calculate the IQR using the 15.5 and the 8, the Q3 and the Q1. So the IQR is showing up at 7.5. Now what we want to do is take that IQR and magnify it or fatten it up by a factor of 1.5. That gives us 11.25. Now we want to develop our two cutoffs. So let's remember the Q1 value is 8. And so we're going to take 8 minus 11.25. That's our lower cutoff. Now that's negative 3.25. I think we're safe to say that there will be no animals in the that are exceeding that lower cutoff. Our upper cutoff is going to be what I get when I take Q3, or the 15.5, and I add on to it the 11.25. And when we do that, we get an upper cutoff of 26.75. And so when we go back to our data set, we can clearly see, right, that any lifespan that's in excess of 26.75 will be declared an outlier. And we can see that although these are close to being outliers, they are not. The elephant, in fact, is the only outlier in this data set. So now using this IQR method, we can technically say that the elephant, in fact, with a lifespan of 40 years, is an outlying value in the data set. Okay, our next subsection, this draws a conclusion to this first subsection on detecting outliers. Our next subsection is on learning how to create what are called box plots, or sometimes called box and whisker plots. A box plot is a graphical display of the 5-number summary for a single quantitative variable. A box plot typically includes a numerical scale appropriate for the data values, a box stretching from Q1 to Q3, a line that divides the box drawn at the median, a line from each quartile to the most extreme data value that is not an outlier, and each outlier plotted individually with a symbol such as an asterisk or a dot. Now, the easiest way to get into this is to look at a box plot that's been drawn for us by StatKey, and then we can go through our list and see how each of these elements is showing up in that box plot. So we're going to go study the box plot that corresponds to the mammal longevity file. This is a data set that we've been looking at several times already in this section. So we're going to go to StatKey, load the mammal longevity file, and study the box plot of the data. Now notice that by default, StatKey always loads the dot plot. But if we go up here, we can see that we can tab between the dot plot, the histogram, or the box plot. This time we're going to study the box plot. All right, let's go through our list and make sure that we see how all of these elements are contained herein. So we said that a box plot should include a numerical scale appropriate for the data values, and you can see the numerical scale down here on the x-axis. That allows us to situate this box plot in space. All right, the box plot should have a box stretching from Q1 to Q3. That's this box that we see here. That's the box that spans the interquartile range from Q1 to Q3. The box plot should have a line that divides the box drawn at the median. So this box from Q1 to Q3, it has a vertical line at Q2, at the median. The box plot should have a line from each quartile to the most extreme data value that is not an outlier. These are the so-called whiskers, and they extend out as far as the data elements that are not outlying elements here. So we see at this upper extreme the 25, and at this lower extreme the 1. Those are not outlying values, and so the whiskers extend all the way out to them. But each outlier is plotted individually with a symbol such as an asterisk or a dot. So since the elephant, as we determined, is an outlier, it appears in the box and whisker plot, but it appears in this case as an asterisk to note that it is outlying. It is separated from the bulk of the data. So that's how StatKey draws the box plot, and that's how we can see all of the elements that we've discussed appearing in this box plot. Now, what I want to try to do with you is draw one for ourselves. I think this is an important exercise because it will reinforce some of the important elements of a box plot. If you draw one or two of these yourself, you will know how to interpret them when you see them. So what I want to do is have us create the 5-number summary and draw the box plot for the following data set. Now, we'll do this together using the overhead camera, so join me at the overhead camera to complete this problem. So there are really 3 steps involved in working this problem. The first thing we're going to want to do is very carefully work out the 5-number summary for this data set. And then we're going to want to look for any outlying values. And then we're going to want to draw our box plot. Okay, so I'm going to do that in this order. I'm going to work the 5-number summary up here. So we've got to fill out our table. We have to find the min, Q1, Q2, Q3, and the max. The min is easy, that's at 38. The max is at 87. The array is 7 columns and 3 rows, so there's 21 elements. And since it's odd, that means there will be a middle element sitting at position 11. So that's going to be 7, 8, 9, 10, 11. And you can see that that fits nicely right in the middle of this rectangular array. And so that's our median at 56. Now, since we have a median in our set, we have to include it in the lower half and in the upper half to do our calculation. And remember that this is going to be in position 11. So that means that the lower half is going to have 11 elements, and therefore there will be a value of Q1 sitting at position 6. So there's our Q1. And we'll also have our Q3 sitting in the middle of the upper half. And again, we can go to position 6 either from the top or from the bottom. And so there's our value of Q3. Okay, so we have our 5-number summary completed. And the next thing I'm going to want to do is explore this data set for any outlying values. And so we begin by computing the IQR, the interquartile range. Let's work that out. The IQR is going to be 59 minus 43, which is 16. I'm going to fatten that up by a factor of 1.5. So that's going to be 1.5 times 16, which is going to give us 24. And I'm going to use that value in conjunction with Q1 and Q3 to develop my cutoffs. So I'm going to take 43 minus 24 and 59 plus 24 to develop my cutoffs, searching for outlying values. Now 43 minus 24 is 19, and 59 plus 24 is 83. And so we're looking for values that are less than 19 or greater than 83. We don't have anything less than 19, but we do have one element that's exceeding the upper cutoff of 83. So 87 is in fact going to be an outlier. And when we draw our box plot for this data, we're going to want to make sure we indicate that. We're going to use an asterisk to indicate that that value is sitting far away from or is outlying from the rest of the data. All right, now, when we draw our box plot, we do want to be careful to try to draw it to scale. So I'm going to use a ruler here just to help me keep things lined up and drawn to scale. It helps to kind of look at your data and realize that, where it's situated. So I have to incorporate values as small as 38 and as large as 87. So I'm going to think of these inches as 30, 40, 50, 60, 70, 80, and 90. So those will be my tens. And I'm going to use major tick marks here to get those tens. And just to help keep things lined up, I'm going to put these minor tick marks at the half-inch points to indicate where the fives are. This will just help locate these data points. All right, so let's remember this is standing for 30, 40, 50, 60, 70, 80, and 90. And that's going to allow me to include all my data points on this scale. And these little half-inch marks are locating 35, 45, etc. Okay, now I always like to begin drawing my box plot by working out the rectangular box that indicates the inner quartile. So I'm gonna find 43 and 59 and draw my rectangular box there. So 43 is just to the left of this 45 tick mark. So I'm going to put my left end of my box there at 43. And 59 is just shy of 60, so I'll put that there. And that box represents my inner quartile range. And then I'm going to divide that box at Q2, the median, which is 56. So the median is going to be drawn in just beyond that 55 tick mark. Okay, so there's my inner quartile range and my median. Now, I want my whisker, so to speak, to extend out to the largest and smallest outlying, values that are not outlying. So for instance, I'm going to go to the left to the minimum of 38. So 38 is right about here. But I'm going to have my whisker that goes to the right only going out to 68 because that's the largest value in the data set that is not an outlying value. So 68 is going to be just shy of 70 here. And then finally, I'll indicate that 87 is in the data set, although it's outlying. I will graph it as an asterisk just to indicate that it's in the data set, but it's kind of removed from the bulk of the data. It's an outlying value. So that's our 5-number summary, our interquartile range analysis, detection of outlying values, and then finally the box and whisker plot, or the box plot that goes along with this data set. All right, so let's return to the class notes. This brings us to our final subsection of section 2.4, side-by-side box plots. The best way to get into this, I think, is to look at a concrete example. So here's a question that might motivate a study. Do men and women run marathons at different paces? So when we look at this question, look at question 1 here. What are the variables that are under investigation? So in this question, what are the assumed variables that are under investigation? Well, one variable is a categorical variable, and that's gender. We're looking at men and women. Another variable is a quantitative variable called pace, the rate at which you run your marathon. Okay? Now, the way the question is phrased, what is the explanatory variable and what is the response variable? So what is implied by the question? So we're wondering if the category, being a man or being a woman, has an effect on the pace with which you run the marathon. So implied in the question is that the category is acting as the explanatory variable and the pace is the response variable. Now, it's very important to get that relationship straight because, as we'll see when we go to stat key, we have to know what it is that we're doing with these variables. So going into this, we're thinking of gender as the explanatory variable and pace as the response variable. Now, we're going to go to stat key and we're going to open up a file. This is a file that I'm not internal to StatKey, so I'll have to load this file. It's data from the 2017 Truckee Marathons, and we're going to select pace and gender for the variables. You'll see how we have to make that selection when we get to StatKey. But we're going to want to examine the side-by-side summary statistics, and then we're going to want to examine the side-by-side box plots. So let's go ahead and open up StatKey and take a look at that data. Now, we have to exercise some caution at this point. In this example, we've got a mixture of variables. We have a quantitative and a categorical variable, so we're going to make our selection here. The file that we're interested in is not native to StatKey, so I'm going to have to upload the file. It is the Truckee Marathons 2017 file. I'm going to load that. And now we can see that this data set contains a variety of different variables. We're interested in one quantitative variable and one categorical variable. And if you look at the legend up here, we're supposed to select our quantitative variable first and then our categorical variable second. The quantitative variable will be highlighted in teal and the categorical variable in gold. So we're interested in pace and gender as our two selections. So let's go ahead and make those selections. And this is what we get. We can see that the pace variable for the males is represented by its own dot plot, and the pace variables for the female is represented by its own dot plot. And we can see those two dot plots side by side on exactly the same scale. We also see in the summary statistics that the standard summary statistics are separated out now according to a male column and a female column, and you also have a column for the overall performance if we just mix the genders back together. Okay, what we're especially interested, though, in this section is the box plots, the side-by-side box plots. And this is very typical to look at box plots side-by-side for comparison purposes. And here we can see the male box plot, the male pace data is in this gold, and the female pace data is in the blue. Now, does this show conclusively that the males and the females are running these marathons at a different pace? Well, that's a question that we would have to examine, study further. But let's just make one observation. I think it does appear to give us some evidence that the men and women at least ran this race at different paces. So one thing we can key in on is let's take a look at Q3 for the men. It's probably just a little bit less than 11. You can see over here in the summary statistics that it's just a little bit less than 11. And what we can say then is that 75% of the men were running at a pace that is less than 11 minutes per mile. Now compare that with the females. Look at the median for the females, right? The median for the females is just a little bit above 11 minutes, right? And what we're seeing here is that 50% of the women, 50% of the females were running at a pace that was slower than 11 minutes per mile. So we have at least that much that we can say, right? That 75% of the men were running at faster than 11-minute mile pace, whereas 50% of the women were running at slower than 11-minute mile pace. Okay, so that brings an end to section 2.4. I hope you've enjoyed this. I will see you again for the next video lecture when we take up section 2.5. So I will see you then. Until then, take care.